This section is going to be kind of similar to the last one. We're going to be talking about how you can estimate a population mean. So we're going to again build confidence intervals, and there's actually two slight variations that you can do. You can either do a Z interval or a T interval. We'll get into greater detail as to what the distinction is, but essentially, if you know the standard deviation of the population going in, that's going to be a Z interval. If you do not know the population standard deviation, which realistically is more common in like the real world, then what you have to do is approximate sigma with S and then build what's called a T interval. So we're going to look at both of those in detail, but the difference basically boils down to, do you know sigma? If so, it's a Z interval. If you do not know sigma, then you make a T interval. So for constructing a Z interval, you first of all have to know the true standard deviation of the population sigma. The population that we are sampling from, it is approximately normal. So you have to know that it's a normal distribution going in, or as long as you have more than 30 or more observations, you can use the central limit theorem and say it's approximately normal. If those are both true, we can make a Z interval for the population mean mu. So what you would do is you draw a sample of size n, find the sample mean x bar, and then that'll give you your point estimate for mu. Then you would calculate the standard error. So the standard error is going to be sigma, sigma divided by the square root of n. Then you pick the confidence level that you're interested in. And like we've done before, we've got a table here. So depending on which confidence interval you want, there is a Z alpha over 2 value that will go with it. The margin of error, that's epsilon. That's going to be the Z value from the table multiplied by the standard error. And for this particular set of problems, Z alpha over 2 times sigma over the square root of n. That will be how you would calculate that. And then the confidence interval is a range of values where you take the mean and subtract epsilon, and then you take the mean and add epsilon. That tells you the spread, of values. So let's just say that we're interested in estimating the population of the mean salary, mu, in a certain city. So suppose we know going in that the population standard deviation is 2,500. Again, in a lot of real world scenarios, you tend not to know the standard deviation of the population. But for the sake of argument, let's just say that we do. So anyway, we're going to draw a sample, n equals 100. Because that is a large sample, large meaning 30 or more, the central limit theorem tells us it's normal with mean mu of x bar equals mu. So we need to find sigma. So sigma over the square root of n, that is sigma x bar. That's the formula that we're going to use for this. So they tell us sigma, which is 2,500. They tell us what n is. So we're going to do the square root of n, square root of 100. The square root of 100 is 10. So you can do 2,500 divided by 10. I don't know how my mouse ended up over there all of a sudden, and that's 250. Okay, so that's that's sigma of x bar. Assume we want a 95% confidence interval. Find the critical value Z alpha over 2. All right, so 95% as a decimal is 0.95. So that means Z of alpha over 2 should equal 1.96. And that's it. So then calculate the margin of error. So the margin of error that's going to be Z alpha over 2 times the standard error, or sigma over the square root of n. We found that from the table before. That's 1.96. We calculated this, sigma over root n, that was 250. So what we need to do is find out what 1.96 times 250 is. That is 490. So the margin of error, that is going to be 490. There you go. Assume that the mean of the sample we collected, X bar, is 40,000. Collect the confidence interval. So it's going to be 40,000 minus the error, which is 490. That'll be the low end. And then if you do 40,000 plus the margin of error, that will give you the range of values. So 40, 490 as the top end. Let's make that look maybe a little more like a 9. So you got a 9 right there. Let's see what 40,000 minus 490 is. So that is 39,510. So then 95% of the samples that we take will have their mean lie somewhere between those two numbers. In the calculator, we're going to go to Stat, go over to Tests, and if we're interested in doing a Z interval, we're going to pick option 7, which is where the Z intervals live. We're going to enter the sigma, the X bar, and the N. We also need to make sure Stats is not highlighted, because you can actually calculate things directly from a list of statistics, which we'll get to later. But here we're just dealing with the aggregated results. So we know X bar, it's 68.5. We have a sample of 100, so that means N is 100. Let's see, we know sigma going in, which is why we can use a Z interval as opposed to a T interval. I'm not sure if they tell us if it's normally distributed or not, but because this is greater than or equal to 30, we can just assume it's going to be approximately normal anyway, regardless of what the original distribution is. And so let's see, we want a 90% confidence interval. So 90%, that's 1.645. So we're going to do Z alpha over 2. That is 1.645. We can just look that up in our table there. And let's see, find a 90% confidence interval. So we're going to go to Stat, go over to Tests, go down to option 7 where Z interval lives. Choose that option. We're going to choose our input from the data, or let's see, we're going to do it from Stats. So arrow over to Stats and press Enter. So we're just going to give them the statistics directly. We're not going to tell them to look at a list of data. We'll do that eventually. So it's 90% confident, 2.8 is the standard deviation, 68.5. So the mean is 60, or let's see, no, this is the sigma. That's what, 2.8. So sigma is 2.8, X bar is 68.5. So this is 68.5, the mean. The N, the number of people we talk to, is 100. And the confidence level we're interested in is 0.90, also known as 0.9. So 68.039 is the low end of this interval. So we're going to do 68.039, and then the high end of this interval is 68.961. So 68.961. So that is a 95% confidence interval. Find a 95%. All right, so we're going to do this once more with feeling. We're going to go to stat, go over to tests, pick option 7. And we're going to change this up to, the other values are staying the same, but we're changing this to a 95% confidence. Whoop, not 85, 95. There we go. Now let's see, 67.951. 67.9. Come on, computer. 951. And then what's the other one? 69.049. So 69.049. That's what it was, right? Yes. All right. So that is that confidence interval. And then we're going to do it one more time, this time bumping it up to a 99% confidence interval, or confidence level, I suppose I should say, 0.99. So 67.779. 67.779. And then what's this one? 69.221. All right, there we go. So you notice that the intervals will get wider. The numbers are farther apart. These are still both 68 and some change. These are a little bit farther apart, but this is just barely above 69. This is a little farther above 69. This is just a hair's breadth under 68. This is a little farther under 68. So the intervals are getting wider as the confidence increases. All right, find the margin of error for each of the confidence intervals above. Okay, well, so if you take the average of these two values, so I'll show you for each of these, 68.039 plus 68.961. So if you add those up and divide by 2, that's going to give you the middle. No, actually, we don't need to do that because we already know what the middle is. The middle is 68.5. What we need to do is we can just take the top of the interval, 68.961, subtract 68.5, and that'll tell you the standard, or the margin of error. So 68.961 minus 68.5. So the error is 0.461. So we'll call that like error 1. And then error 2, you do like 69.049 minus 68.5. So 69.049 minus 68.5. That is 0.549. Call that epsilon 2. There you go. That's that one. And then this one, we're going to do 69.221, subtract 68.5. 69.221 minus 68.5. That is 0.721. That's the margin of error for this one. All right, and then let's see here. It is found that the mean height of men is 69.3. Is it reasonable to assume that men with the medical condition are shorter than the mean of the general population? Excuse me. So let's see. So you notice the highest we get is 69.22, and they're saying 69.3. That is above the 99% confidence interval. So then, is it reasonable to assume that they are shorter than the mean? So yes, that is a reasonable assumption, because if the general population is 69.3 and we're still not even there with our widest distribution, that implies that yes, people who have this medical condition are going to be shorter. All right, what else do we have? So same kind of scenario, find a 90% confidence interval for the population mean with this medical condition, round to the nearest whole number. Let's see. So we actually already did that. This, if you round this off, it's basically from 68 to 69. So the scenario is in no way different, but we're just going to say 68 to 69. That's if we round to the nearest whole number. All right, determine the margin of error from part A, round to 1 decimal place. So if you do 69, the high end number, minus the average, 68.5, that is going to give you an epsilon of 0.5. That is indeed 1 decimal point. So it's basically off by about ½ an inch. What's the smallest sample size n that would produce a 99% confidence interval with that margin of error? So the formula we need for that, n is equal to, we had that in the previous section. Let's look up that formula here. So it's z alpha over 2 times epsilon over the error. Let's see. So it's z alpha over 2 times sigma over the error. You take all that and you square it. So for 99%, we're going to use this, 2.576. We happen to know sigma, which is 2.8. And then we're going to divide that by the error, which is 0.5. Capital E and epsilon are the same thing. They're both referring to the margin of error. And you take that and you square it. So let's find out what that is. So we're going to do 2.576 times, what was it, 2.8 divided by 0.5, and you're going to take that and you're going to square it. And that's 208.098. 208.098. You're always going to round up to the next whole number, which means you're going to need to have 209 people in your sample. All right, let's see what else we have. So t distribution, it's a variation on a z distribution, and it depends on how many values are in your sample to begin with. So one of the reasons why t intervals exist is they allow you to do statistical calculations based on numbers of data that are smaller than 30. The reason, by the way, that 30 is a significant number, the reason why that's a cutoff is that by the time you get a t distribution of 30 or more data values, it's approximately equal to the z intervals if you go out like 4 decimal places. You could try to get more precise than that, but generally 4 decimal places of precision is plenty for our purposes. So anyway, it's based on the number of data, which is actually the term we're using is the degree of freedom. So the degree of freedom is just n minus 1. So if I have 12 things in my sample, the degrees of freedom is just 11. If I have 8 pieces of data, the degrees of freedom is just 7. It's just 1 less than however many things I have in my sample. So what you would do is to construct a t interval, you don't know the true population standard deviation. You either know that it's normal or we're working with a large sample, which is greater than 30. If either of those is true, we can say it's approximately normal. If these are both true, we can construct a t interval for the population mean as follows. It's very similar to the z interval process. So what you would do is you would draw a sample of size n, calculate the sample mean x bar. Then you would have to calculate the standard error. The way you would do that, since we don't know the population standard deviation, we have to approximate it by doing s over square root n. And s is the standard deviation of the sample. And then you pick a confidence interval. You pick, instead of a z alpha over 2, it's actually t alpha over 2. And so, like I was mentioning before, that's based on degrees of freedom, which is just 1 less than the sample size, n minus 1. You can find t alpha over 2 with the calculator. And so the margin of error is t alpha over 2 times the standard error, or t alpha over 2 times the standard deviation divided by root n. And then you make the confidence interval the same way as before. Take the mean, subtract your error, take the mean, and add the error. That tells you the range of values that the actual mean is going to be inside of, like 95% of the time, or whatever confidence level you pick. So we're going to go to tests in the stat menu. This time we're going to pick the very next option, which is a t interval. We got to give them s, we got to give them x bar, we got to give them n, and we have to know the confidence level beta. And again, this is a very similar process. It's just this time we're doing the t interval. All right, so students are taking a test worth 200 points. We have a sample of 36, so that tells me n equals 36. We know X bar, that's 112. We know S, that is equal to 30. Should we use a Z interval or a T interval? Well, the answer is a T interval. And the question is why? Because we don't know sigma. We know the standard deviation for the sample, which is S. We do not know the standard deviation for the population, which is sigma. So next, they want us to calculate the standard error. So what we're actually going to do is we're going to start with the confidence interval first. So let's start with that, shall we? So we're going to go to stat, go over to tests. T interval is option 8, so we're going to pick 8. We're going to get the data from stats. We're just going to tell them directly what the values are. So what? S is 30. That's what this is. S is 30. Here they call it S sub X. Let's see. X bar is 112. This is 112. The value of N, that's going to be 36. That's how many people are in the sample. And let's see, confidence level is 0.95. That's the confidence level we want. All right, so it gives you the interval, it gives you X bar, S, and N. So 101.85. Let's write that down, 101.85. And then we're going to do 122.15. Okay, so that is the confidence level. Oh, and then actually this is the standard error. So the standard error is, let's see. So the standard error is S divided by square root of N. That's not what I want. I want this right here. So this is S over the square root of N. So S is what, 30? And then you divide that by the square root of N, so you divide that by 36. The square root of 36 is 6, 30 over 6. That happens to give you 5. So that's the standard error. All right, same scenario, find a 99% confidence level. All right, so let's go ahead and do that. Stat, go over to tests, pick option 8. We're going to change the confidence level to 0.99. $98.381. 98.381. And what's the other one? 125.62. And let's see, that actually is supposed to go up here, but that's okay. So that goes up there. Let's see. What's the margin of error? Well, if we do 125.62 and subtract 112, that will tell us the margin of error. So 125.62, subtract 112, and you get 13.62. All right, there you go. So that's the margin of error epsilon, 13.62. So there you go. There's your margin of error. And then this, as I said, that's the answer to part D, which should actually be up there. But anyway, let's see. What else do we have? Assume that IQ scores of college graduates are normally distributed with a standard deviation of 15, just as in the general population. A researcher would like to determine if the mean IQ is higher for college graduates than the general population. We have a sample of 20 college graduates. The mean of the sample is 112. All right, so this is 20. That's N. X bar is 112. That's the mean of the sample. They say the standard deviation is 15, just as in the general population. So that basically means they're telling us the standard deviation for the population, which is 15. So that is a very crucial piece of information. So that means we are actually going to use a Z interval because we know sigma. We know the standard deviation for the population. So we need the standard errors. The way you find the standard error, let's go back, find the formula for that. Let's see here. So it's just sigma over square root of n. So the standard error when it's a Z interval is sigma over the square root of n. So it's actually the same formula because it's either S over root n or sigma over root n. Just depends on which one you know. So this is 15 divided by root n is 20. Let's find out what 15 divided by root 20 is. That is 3.3541. Okay, that's your standard error. Find a 95% confidence interval. All right, we can do that. Stat, tests. We said this is a Z interval, so we're going to pick option 7. Sigma was 15. X bar is 112, which is actually what we already have. This is 20. Let's see, what do we want? We want 95. All right, 0.95 it is. 0.95. You go ahead and calculate this. 105.43. And then the other end, we're going to have 118.57. Okay. So that's your confidence interval for that one. Oh, and by the way, even though we only have a sample of 20, because we know going in that it's normally distributed, we can just treat it as normally distributed, even though it doesn't meet the condition of having at least 30. Because if we know it's normal, we can just go with that. The 30 is just a check to say, is it okay to approximate it as being normal, as opposed to something that's already normal and it doesn't matter. All right, find a 90% confidence interval. This is going to be much the same. We're going to do stat, go over to tests, pick option 7, change our confidence level to 0.9 or 0.90. You get 106.48. And then on the other end, we have 117.52. All right, there you go. Based on the 90% confidence interval, can you infer that college graduates have a higher population IQ than the general population, which is 100? Well, It's pretty darn likely that they're between 106 and 117. So the answer is yes. 90% of results are between 106.5 and 117.5. So, yes, that is a valid conclusion to make from those statistics. Okay, so here, this one's a little bit different. Here, they actually give us the original data that these came from. So we have 12 students, we've got some data, and they do tell us that the test results are normally distributed. So even though we have less than 30, we know that the distribution they're coming from is normal anyway, so we don't have to fret about having a small sample size. So find the sample mean X and the sample standard deviation S. So let's put this information into the calculator. So we're going to do stat. I'm going to choose edit. And let's go over to list number 1 here. We're going to clear this, press clear, and then enter. Let's see. So what are our numbers? 1424. 1424. Then what? 1223. 987. 692. 947. 723. 837. 721. 747. 540. 623. And 1445. Okay, so then we're going to go to stat, and let's see. We're going to do that eventually. Let's see what they say. Find the sample mean, X bar, and the standard deviation. So, let's hang on one second. Do we need to use a T interval or a Z interval? Well, the answer is a T interval. The reason why? We don't know sigma. Nowhere in there do they tell us the standard deviation of the population. So since we don't know sigma, we use T. And I guess we can use one variable stats with this. Let's just go ahead and do it that way. So we're going to do stat calc, pick the 1 var stats. We're going to do list 1 is where I put the data. If there's something in the frequency list, delete it. Because we are not doing a frequency distribution. We're only doing one list of data. If the frequency list is filled in, it's going to mess you up something fierce. So we calculate this. So X bar is 909.08. So X bar, that is 909.0833. S. So that's kind of a clue which one we're looking for. So this is S right here. 305.2657. So 305.2657. Is that right? 2657. Okay. So that's X bar, that's S. We already did this. Calculate the standard error. So that's going to be S over the square root of N. That is what standard error equals. So S is right there, 305.2657. We're going to divide that by the square root of 12. So let's see what that is, shall we? 305.2657 divided by the square root of 12. 2657. All right, so we'll do that. 88.12 is what that is. All right, so that's that one. Find a 95% confidence interval. All right, so here's how this one's a little bit different. So we're going to go to stat. We're going to go over to tests. We said earlier we're going to use a t interval because we do not know. We don't know the sigma. So then here's what we're going to do. We're going to go over to data and press enter. So it's going to look for the list. Frequency is just 1. Confidence level is 0.95. And actually, what you might have noticed is if you go over to stats, since I calculated the 1-bar stats, it's actually filling all these in automatically, which is kind of nice. If you didn't calculate them, you could also do it this way. Let's see, what's the confidence level? It's 0.95. So this is going to be what? So this is going to be, you notice this also tells you X bar and SX. It tells you what they are anyway. 715.13. So, okay, 713.15. And then the high end is 1103 exactly, which is kind of interesting. All right. 1103 it is. Find a 99% confidence interval. All right, we can do that. Stat, go over to test, choose option 8. We're again going to do the list 1 data. Frequency is just 1. 0.99 is the confidence level. And let's see, what is that? 635.39. And then what's this one? 1182.8. 1182.8. All right, there you go. That is the confidence interval for that one. All right, so that, my friends, is the end of chapter 9. And we've got only one chapter left. And then that'll be the entire course. So, so there you go. I mean, you'll have like tests and stuff, but that'll be all the lecture material. So I will see you all then.